So I shall start now. Okay,
Yes,
good afternoon, everybody.
good afternoon, sir.
I would like to thank HarperCollins for arranging this demonstration program. My primary aim will be to show the teachers who will be joining this program how science learning can be made enjoyable and also theories understandable. When classroom teaching, learning goes on with experiment and activity, not in the lab, but in the classroom, when the day-to-day science teaching is done, how that can be made enjoyable and also understandable. The theory is understandable clearly when experiment is done, and all the experiments that I shall do will be low cost, no cost experiment. Things which are thrown out, those are types of things also will be used. I'm a very young man of 89. I take up all these programs over the country because I'm concerned about the future generation. What kind of earth I am leaving behind? The climate change, the global warming, climate change, and now this pandemic that has come. What kind of first earth? And the teachers are said to be the change makers. A child is in the hand of a teacher from class 1 to class 12. And if the teacher wants, she or he can change the world by changing the mind of the child who is with them for 12 years. And it is necessary to change the world. Earth has got a very difficult disease that has to be cured. Now, my slogan is where there is no laboratory, how science can be learned by doing. There is a Chinese proverb which says, I read, I forget. I see, I remember. And I do, I understand. Science is doing. So what I shall do, I shall do some experiments in physics, which is say for 8, 9, 10, 11, like that. Experiments on, say, air pressure and also on magnetism, depending upon the time that I shall have. So I shall start first with an experiment with a bottle, a little water, a matchbox, and a piece of paper. And I need some water. So what I do, I take some water in this bottle. About a cup of water. About a cup of water. Okay. So I've taken about a cup of water. And then I close it. I close it. See, it's transparent. It's transparent.
Can you keep the bottle towards you so that we can see the entire bottle?
Okay.
Yes. Perfect.
Now, you see, it's transparent. I press it hard, quickly. It's still transparent. Okay. I leave it. I press, I leave. I press, I leave, but transparent. Now what I do, I shake it. Transparent. Now what I do, I shall light a piece of paper and then put it inside. And then close it and do the same kind of operation. Press and release and see what happens.
If you can keep the bottle towards you, sir. Yes.
Okay. Now what I do, I drive away the smoke. There is no smoke that is coming now. I close the bottle again. I close the bottle and then I press suddenly. You see, it's transparent. Sudden release. See, it becomes smoky. I now see what is coming out from the bottle when I press it. Can you see the smoke coming out?
Yes, yes.
Now I drive away all the smoky things. Then I again close it. I have driven out all the smoky thing. Then I do it again. Press, release. Press, release. You see, it has again become smoky. And you see again, smoke-like thing will come out. Can you see the smoke-like thing?
Yes, yes.
Now, my question to a teacher, what is coming out? What is coming out?
Okay, so let's take this answer to any teacher.
Yes, any teacher, one teacher. What is coming out?
So teachers, you can choose to type your answer, or you can choose to show up your hand and we can unmute you so that you could answer. So I repeat, the question is, what is the white color flame, the smoke that is coming out?
What is smoky-like thing coming out? Smoke-like thing coming out. What is that?
So looking for answers. Okay.
Okay, let me start because there is very little time. So let me
we've
explain.
got an answer, sir. We got an answer.
Yes, let me hear.
Srijita ma'am says air. Navdeep ma'am says vapors.
Yes, let me hear.
Air or vapors?
Hmm?
Air.
Air.
Yeah.
Air. We don't see air. Air is there in this room. Do we see the air?
So someone is saying water vapor.
Water vapor. Now, when you stand before a ocean or a pond or a river, do you see water vapor coming out? But water vapor is constantly coming out. When you put a wet cloth on a string to dry up, do you see the water vapor coming up? It gets dried up after, say, maybe 2 hours, 3 hours on sun. But you don't see water vapor. Water vapor also cannot be seen. Okay. So it's not water vapor, but it has got something to do with water vapor.
Someone says
but
CO2.
It's not simply water vapor.
Carbon dioxide.
Carbon dioxide. Okay, let me see. Look at my hand. I am blowing air from my mouth. Do you see the air that is coming out? What is coming out from my lungs?
Carbon dioxide, CO2.
Carbon dioxide. Do you see the carbon dioxide?
No.
No, you don't see carbon dioxide. Hydrogen, oxygen, nitrogen, you don't see.
They're saying it is fog.
What is coming out then? Now it has got, I told you that it has got relation with water vapor. But that paper that I had burned and I had introduced inside, that has got to do something with the water vapor. So when I burn a paper, a smoke is produced, of course. Smoke is nothing but particles. Smoke is nothing but particles. Carbon dioxide is produced. That I don't see. That is coming out. But the smoke that we see are the carbon particles. So this place has got carbon particles. But when I had shaken the bottle with water, lot of water vapor was there. Okay. And then when I suddenly press, when you teach class 11, 12, you say this is adiabatic compression. And when I suddenly release, adiabatic expansion. When I suddenly press, then it is heated a little more and a little more water vapor comes out. So this place is more or less saturated with water vapor. And I have given a piece of burning paper. And paper, it has released certain carbon particles. When I suddenly release, then adiabatic expansion takes place, then the gas which is there inside, the water vapor, it cools down. When it cools down, then the water vapor accumulates around the carbon particles and water droplets are formed. So what I have done really, I have created fog or a cloud inside the bottle. The way clouds or fog is formed in nature, in the same way, I have formed cloud or fog inside the bottle. I needed simply a bottle and a piece of paper and a matchbox to show this. And when a teacher has to teach clouds, fogs, and all this during in the school, they can do such experiment in the classroom, and it's so enjoyable for the child and so easily to understand. So So this is the first experiment. When I so what is coming out is then the cloud which is coming out, or the water droplets which is formed like cloud or a or fog. That is what is shown here. Okay, this is the first experiment. Not on air pressure, of course. Pressure is there, so we have to understand what is pressure. Why we have to understand what is pressure. That's the first experiment on pressure, to explain what is pressure. Now let us understand what is pressure. Pressure is I can understand force. So this is a glass bottle. This is a glass bottle, and if I give a force to the glass bottle, it moves. It moves.
So can you keep the glass bottle towards yourself, sir?
It's here.
Little back, even towards. If the camera can
give
be
me another piece of book. Another piece of book. Okay.
Yeah.
Here. Okay. So when I apply a force, it moves.
Yes.
But pressure is force per unit area. That's an abstract concept, and to understand an abstract concept for a child is quite difficult. So I shall give you an idea of how you explain pressure. Okay. Okay. Let me show you. Okay. Let it be here like this. Okay. Okay. Give me another book. Okay. Now, what I have got taken a pen. I know pen. This
can you
area.
keep the glass a little bit back, sir?
Yes, I shall take like.
Or if you can take another book, because keeping a book.
Another book. Okay. Keep no.
That will do.
Yes. I'm putting another book. Okay. Now here. Is it all right now?
Yes.
So I'm applying force. It moves. Now here I'm taking a pen, and you see this area of this, and when I open it, and the area of this pen, dot pen, this area is very less compared to this. Okay. What I do now, I take a piece of just newspaper, close it tightly, hold it tightly, and hold the wider area on the piece of paper. And then I put a book over it very slowly. So the book has weight, which is acting downward. That's the force of gravity is pulling this. So that's the force which is applied. Now, what I shall do, I shall put this wider area first over this paper and put it slowly. So let the force be F. Force that is being applied on the top is F, which is applied here. Now this is the wider area. Now what I do, I open it up. And now I'm taking the pointed end and place it here and place the same weight over the book, over the paper. See what happens. See, it has become pierced. Okay. The same force which is acting downward when the area is big, it did not. When the area is less, so force per unit area is pressure. Remove this book, remove these two books. And you all do it in the classroom. You explain like this. P is F by A. P is F by A. If P is F by A, then F is P into A. That is what the children learn in the classroom. And to make a child understand about pressure, you can do this experiment. Now you have to understand how the air pressure is created. This is there is air in the room, but I don't feel the pressure. I don't feel the pressure. I don't see the air. Also, I don't feel any pressure. Now see here in these glasses. Give me the books again. Give me the books again. Okay. Now, the pressure that is acting now inside the glass, at the bottom or at the side, is by the molecules of air which is there inside the glass. Okay, the molecules which are there inside the glass, that applies the pressure on the A or the side. Now let me take a, now what I do, suppose there are 100 molecules inside, and those molecules at this room temperature, say about, say 23 or 24, 25 degrees Celsius, are they stationary? No, they're all moving. They're all moving. At what temperature, all this movement, which has kinetic energy, when all this movement will become zero, or there will be no movement. At, we all know, at 0 degree Kelvin or minus 273 degrees Celsius, all the movement will stop. And as you raise the temperature, the molecule starts moving. Molecule starts moving, and it goes on hitting the books. It goes on the table, on the walls, and at the bottom of the glass or the side of the glass, and that gives the pressure. That gives the pressure. Now suppose there are 100 molecules inside, and I close it. Then also 100 molecules. The air molecules which are there, up there, or here, there, they are not really hitting. The probability of the molecules hitting the glass bottom inside is what this 100 molecules which is inside. Say there are hundreds, not millions of molecules inside, but those are the molecules which is there inside the glass. They are hitting the bottom, and that, because of that movement and the hitting, that creates the pressure inside it. So pressure now, which is normal atmospheric pressure, now I close it, 100 molecules, temperature remaining same, pressure remains same. This is what you have to first understand, make the child understand. Okay, now I shall take up an experiment. We have understood what pressure is. Yes, bring. Now what I shall do, I shall again take a bottle.
Sir, one request.
Yes. Yes.
There is a teacher on Facebook who hasn't understood what the what P, F, and A in the formula denote.
F is the force. F is the force. A is the area. P is the pressure.
Wonderful, sir.
So F is equal, P is equal to, pressure is equal to force per unit. If on A area the force is F, then on one area the force will be F by A. The simple arithmetic, So if on A area force is applied is F, so on unit area 1, the apply will be F by A, and that is P. P means pressure. Okay.
Thank you, sir.
So, so now what I do, I take where is the funnel? Yes, here. I take hot water inside this. A little bit of hot water inside this. I've taken hot water inside this. That's all right. Okay. Okay. I start to give a little more. That will do. So I have taken hot water inside this, and then what I do, I close it, and then shake it. Then throw away the water, and then close it again. See what's, can you see what is happening? It's getting pressed. Am I pressing it? No, I'm not pressing it. You see what is happening. Now what I do, put this one, this one, up there. No, now see, it is already getting crushed. I am not pressing. Who is pressing? Yes. Who is pressing? Air is pressing. Now you see, what I shall do, I shall put in water, cold water here, quickly. Come this way, I'm putting cold water. It gets completely crushed.
Yes.
Who is crushing it?
Atmospheric pressure.
But how?
How?
Atmospheric pressure was acting before also. When no hot water was given, atmospheric pressure was acting from outside, and the same atmospheric pressure was also inside. I have shown you when I close it without hot water. Whether it is open or closed, pressure is same. So pressure outside from this side and also pressure inside acting outward on the wall, same. So nothing happens. But now why it is crushed?
Okay, so here we got an answer from Madhuri ma'am on Facebook.
Because
Vapor in the bottle, yes, vapor in the bottle is getting condensed, and so pressure inside is less, and atmospheric pressure is more from the exterior.
Exactly. When the inside, when I put in warm water, hot water, then the air which was there, that was expelled, and this place is full of steam, water vapor, steam. It's hot steam. So when it gets cooled, then this steam, it condenses, water vapor condenses, and then pressure starts going down. When the pressure starts going down, gradually it is crushed by the air pressure from outside, which is more than the pressure inside. And when I put in cold water, what happens outside? Then the inside gas is getting cooler very quickly. So the water vapor, becomes water. So the vacuum is much more. So it gets completely crushed. When I started maybe 75 years back, then it was shown with a 5 liter mobile tin. So I use only this, which is thrown away. I tell in my workshop with the teachers that if all the students of India, crores of students of India are given bottles, 10 bottles of that I use in my workshop, that you use in the that is needed in the classroom teaching, then perhaps a little bit of plastic pollution problem can be solved, can be usefully used. It's fully used.
Recycled also.
Okay, so this is the experiment that I wanted to show you. Now, the next experiment. Now. So now see how simply I can make the child understand. Now, here is the plunger. This is open at this end. At this end, it is open at the nozzle, and also it is open at this end.
Yes.
Okay. So air pressure is acting on this side. Normal atmosphere is acting on this side. So plunger remains at the same place. But plunger remains at the same place. Now see what happens. Now when I put the plunger here and close this one, tell me, is there any air here?
Not necessarily, no.
See it very intently. Is there? Very little here.
Yes,
Very little. Yes. And now when it is open, what is the pressure acting on the plunger? Normal atmospheric pressure, because it is open.
Yes.
Now we close it. What is the pressure acting on the plunger? I have shown you with the glass. What is the pressure now? Same. Normal atmospheric pressure.
Yes.
Okay. The air which is here is not striking the plunger. Air which is there inside this small piece, the air which is what is there, that is striking. And that is because of that pressure is created on the plunger. You close it, the same number of molecules. So pressure is same. The explanation that was given with this glass.
Okay.
Now see what happens when I pull it. When I pull the plunger and leave it, see what happens.
It goes back. Yes.
Who pushes it?
Pressure.
From
Vacuum.
This side.
Yeah.
From this side. From this side, air pressure pushes it. So that means that when I pull it, definitely what happens to the pressure here? Does it remain same? It becomes more or less than the atmospheric pressure, which is acting from this side. Is the pressure same?
The pressure
when it was like this, the pressure here was normal atmospheric pressure acting on the plunger. Now when I pull it, it is going in.
Yes.
Is the pressure same now when I pull it inside?
It is less.
Must be less.
Yes.
That is the reason why the air pressure from this side is pushing it. Okay, why it is getting less? Because this much of air has expanded and it has got now much more area to strike. Much more area to strike. That's the reason pressure is going down.
Okay.
You can give an example, you can give an analogy to the students. You tell the students, suppose you have decided to have music and dance on 31st December night, and it happened to be a new moon day, Amavasya day, new moon day, and you decide to have fun. When the bell rings at 12 o'clock, you suppose 50 or 60 children are assembled in the room. There is no table or chair, and when it strikes 12, then you all starts music and dance. So when you start dancing and dancing, then suddenly the power goes up. It's a new moon day. There is no light, so pitch dark. Nobody can see even their hand. But then, in joy of the New Year's Day, they're all dancing. What will happen? Some of them will go and hit the wall. Let 10 children hit the wall, and because of that, there will be pressure on the wall. Pressure is only force per unit area, so there is pressure on the wall. Now, suppose the same number of children is there in a very big room, 10 times larger than that in length and breadth, and the same number of students start dancing, and the light goes off, and they go on dancing. Will the heat on the wall remain same, or less, or more? When the room is very big, the same number of students dancing, light goes up, and if the heat on the wall will remain same, less or more?
It should be more.
It will be more. Only 10 children, the same number of children, but the room has become very large.
The pressure
You have
is
lots
less
of
in a
space
bigger
to
room.
dance. Huh?
The pressure is less in a bigger room.
Pressure will be less because the number of children that will hit the wall will be less because the room is very big. So chances of hitting will be much less. So the pressure also will go down. The same thing is happening here because when I pull it, then the area is becoming where the air molecules can strike becomes more. So now with this same thing, we can understand more. How is it? When I pull it now and it goes in, that means air pressure is acting from this direction.
Yes.
When it's like this, I pull it. Air pressure acting in this direction.
Exactly. From all the directions.
What does it prove? Air pressures from all directions.
The directions.
Okay. So with this simple syringe, I have with me 20-30 syringe. If any of you want syringe, I can provide you some. Okay. Whenever somebody comes to take injection, every 2 months I have to take blood samples. So next, what I shall do, I shall show you another experiment. Here.
Sir, can you use the book, sir? Can you use?
Yes, can you use the book? Please put the books here. Okay, yes. Now you can see. Okay, fine. So here in this balloon, I have taken water. And there is a reason why I have taken water. How do I fill it with water? I take this before a tap and put it on the tap like this. And then because of the pressure, because the tank is up there, so the pressure is quite high. So you can, but you can't put water with syringe or with a mug. Then you can't inflate it like this. When the pressure is very high, then the water can enter and you can inflate it as much as possible till it bursts. So now it places well over the mouth of this glass bottle. When I press it, you see it does not go. It just flattens out. It does not go in. I'm pressing vertically down. Okay, it just doesn't go. Now what I shall do, I shall light a piece of paper, put it in, and then put the balloon over it. See what happens. Yes. Now. Yes. No. So these days, these matchboxes are also so spurious.
Understood.
Yes. Now it's working. Okay, now light it. Leave it, leave it, leave it. So I'm placing it. See, it has gone in.
Wow.
I was trying to push it down, it does not. But now when I put the burning paper in, it's as if it is pulled in. Why does it go? Let me hear from a teacher. Why does it
So
go?
teachers, there's an interesting question. All of you have seen the experiment, and how did this magic happen? Any answers? Anyone would like to speak
When
up?
I press it, it does not go.
Yes.
But when I put the burning paper inside and press it over it, and but you have noticed also, when the paper
sir,
was burning, it did not go.
We got
When
an
the
answer.
paper starts going to be extinguished, then it starts going in. And when the paper got completely extinguished, it just as if it is pulled in.
So Sunaina ma'am wants to answer it.
Yes, please do.
And I'm unmuting Sunaina ma'am.
Yes.
Ma'am, please unmute yourself and you can answer. Yeah.
Okay,
Yes.
Thank you so much, sir. Good afternoon, sir. It's Sunaina here.
Good afternoon.
I'm a
Good
physics
afternoon.
teacher,
Yes.
physics teacher from Jalandhar, and we usually do perform all these experiments. And as you were explaining, initially it was not going inside, but as you have blown up a piece of paper, so hot air has rushed out, and due to atmospheric pressure, it is being pushed inwards towards this container. Thank you, sir.
Okay. No, just 1 minute more. You are absolutely
yes,
right.
yes.
When I put in the burning paper in, the air gets heated and it goes out. It goes out.
Yes.
But you have
Yes.
seen, you have observed that as long as the paper was burning, it did not go in.
It didn't
When
go
the-
in. Yes.
Why is it that when the paper got extinguished, it goes in? Why?
I think we can relate it to this thing only that a lot of air, which is, we know that as the hot air always rises up, and when it was burning, there was
That's
still,
not for
Yes.
that the air goes out. The hot air or air inside goes out. But
Yes.
when the paper is burning, all the air is going out. So
Yeah.
why it is not going in?
uh,
Because the number of air molecules have become less.
yes,
But then the temperature is very high.
yeah.
When the temperature is very high, what about the molecular movement? Are they slow or they are fast?
When temperature is high, it's
They
quite
are very
fast.
high. So
Yeah.
the pressure on the wall is very high. Pressure on the balloon is very high. That's the
Very
reason it's not going down. But when the paper gets extinguished, then it starts cooling. When it's
Yes.
cooled, then the pressure goes down. Then the air pressure forces this
pushing
in.
it downwards.
But the question is, I can't press it in. Why the air pressure forces it in?
Yes,
That you
was-
can. That you should answer from this experiment. What I did.
Yes.
Tell me why.
Okay, because again, sir, the atmospheric pressure is a lot of a huge pressure, and the inner, as there is no air inside the container, it is not going to balance it. So that's why.
No. What I showed you, pressure, is it only from top to bottom or this side, this side,
From
this
all
side,
sides,
from
all
all
sides.
direction?
All
So the
directions.
pressure is acting from all direction.
All directions. Yes.
And that's the reason why it is going in. It is squeezing the balloon to a smaller size.
Yeah.
If I had a slow motion camera, you can show you that it's squeezing and it's going in.
Yes.
Because the air pressure is acting from all sides equally
Yes.
and it's going in. Okay? So this is a
Thank you,
very,
Sunaina, ma'am.
Thank you. Thank you, sir.
is a very interesting experiment for the children.
Yes, sir.
For the
yes.
children.
Thank you.
Okay, let me see what next I should show. Acha. Next. Balloon sucked in. Acha, now, okay. You can show a very interesting experiment, which the principle is used by the magician Pishi Sarkar. Pishi Sarkar's magic's name is Water of India. Water of India experiment. So what I shall do, there is a hole here. Can you see the hole?
Yes.
See the hole. And also there is a hole here inside in the bottle. Here.
Yes.
There is a hole here.
Yes.
Okay.
You can see it, sir.
So
Yes.
what I do, I shall take water here inside and then I shall turn it round. Water will start falling. Then I shall order, water, you stop. And the water will stop falling. So you see this. Hmm. Water, you fall. Pani band ho. Pani giro. Pani band ho. Jal poro. Jal band ho.
Wow.
When I close it, it stops. But watch. Does it stop immediately I close it, or it takes a fraction of a second or fraction of 2 or 3 seconds for it to go? See now, the water is falling. I close it. Water falls. I close it. Does it stop immediately or it takes a little time?
It stops instantly. That's
It's
what I
not
see.
instantly. It takes a little time. Achha, if it takes little time, what happens to the level of water? Does it remain same when I close it immediately? Does it remain same, or it goes down or goes up?
What do you do
Now I
again?
close it. It is go
It
down.
remains same.
It will
Okay.
remain same. Why it will remain same? So if when I close it, just then the water is falling. So this level will go down a little,
Okay.
isn't it?
Okay.
When I close it, the water goes on falling for a fraction of a second or so. So
Okay.
when the water starts falling for a fraction of a second, so what happens to the level of water? It will go down. So
It
what
should go
happens to
down.
the enclosed air? What happens to the enclosed air? It expands. If an
Yes.
enclosed air expands, what happens to the pressure inside? Goes down.
Okay.
I have shown other experiment that
Yes.
if it expands with the syringe, I have shown you that when the
Yes.
air expands, the pressure goes down. So when
Yes.
this pressure acting downward plus the water pressure is equal to the air pressure from bottom, when they are same, then it stops. At the beginning, this is air pressure, it is open. So air pressure plus water pressure, and this pressure is only air pressure upward. So it
Okay.
falls. Okay. So this is on P.C. Sarkar's Water of India experiment. Okay.
Water of India.
Okay. Water of India experiment.
Why
Now,
did they call it that?
yeah.
Why did they call it Water of India?
That's what he has named, Water of India experiment. What P.C. Sarkar has named. I don't know why he named it like that. Achha, now an experiment which have been done, all of you have learned in the same way. You take a glass of water and then I take a glass of water. Yes. Take through to the beam. The books which I have studied, which you all have studied, keep it here. The book said that take water full to the brim so that no air is left. I think you remember this experiment. And then you turn it over, put a card over it. So I have put a little heavier than card. This is plastic, but heavier than a simple card. This is a simple card, but this is heavier, a little heavier than that. And I turn it over. The book says that you have taken water full to the brim so that no air is left, and you release your hand, it does not fall. Why
Yes.
it does not fall? Why it does not fall?
Again, pressure.
The pressure downward
Upward.
and pressure upward must be same.
Yes.
Okay, but look, when I release my hand, this is really floating. Can you see it is floating?
Yeah. It is moving. Yes. Yes.
That means it has gone down a little.
Yes.
See, you take any amount of water. I take half. And when I used to ask the teachers or the students, what will happen now? There is so much of air inside. And when I release my hand, what will happen? Will it stay or fall? There is so much of air here. It does not fall.
Stays.
It does not fall. It does not fall. No matter how much water you take, no matter how much water you take, it will not fall. It will not fall.
Yes.
Why it is not falling? The reason is same as the Water of India experiment. Now, when it is like this, what is the pressure acting on the water surface?
So we have an
Normal,
answer here.
normal atmospheric pressure. Okay. Normal
Okay.
atmospheric pressure is acting. Now you close it. What is the pressure acting now on the surface of water?
Again,
Whether it is
downward.
open or closed. What is the pressure now? Normal.
Normal.
We have discussed. Normal atmospheric
Yes.
pressure, whether it is open
Yeah.
or closed, because number of molecules are same, temperature is same, pressure remains same. Now I turn it over. Same air goes up, you see, the same air is going up. So this is normal atmospheric pressure plus the water pressure is more than the pressure acting upward. So what will happen? This card will start going down. When it starts going down, then this level of water, will it remain same? No. What will happen? It will also try to come down.
Yes.
So the enclosed air will expand,
Yes.
pressure will go down, and when the pressure, this reduced pressure plus this water pressure becomes equal to the upward pressure, then it does not fall. That is what is happening. And this was when we did this quest program for 5 years, we could not give this experiment, couldn't show it because we are not understanding at that time why it is not falling. Then a class 11 student gave us the reason. You see this now. I shall show you what he said. He said that take a glass, make a hole below, so that you have the water will start falling. The water starts falling, and you close the hole. I close the hole. I close the hole and place this card over it. I have closed the hole, place card over it, turn it around, and I'm keeping it closed. Oh no, no. Okay, I've kept it closed. As long it is as long I keep it closed. Now let me show it again. Where is the hole? Yeah, here is the hole. Give me water here. That's all right. All right. Acha, now I have closed the hole and I leave my hand. Oh, it does not fall. I open the hole, see what happens. Immediately I open the hole, it falls down. What does that mean? When I open the hole, it becomes normal atmospheric pressure acting downward. Normal atmospheric pressure acting upward. Because of the weight of the water, it falls down. This pressure, when I open the hole, what has happened? When I release my hand, the level of water has gone down because at the beginning, let us understand it properly. Let us understand it properly. Come on, please give me water here again. Okay. Now the same air is going up. Okay. The same air is going up.
Okay.
I am now, the pressure here is normal atmospheric pressure.
Okay.
And plus this pressure of the water. These two are more than the pressure acting upward. So when I open that hand on the top, just a minute. This hole is not properly closed by my finger.
Okay.
Let me see. This hole has not been properly made. Okay, let me see again. Now, experiment in science, theory and experiment must go together, and experiments have failed. The Large Hadron Collider experiment in CERN that failed. After 6 months, it was done again. Then the Higgs boson experiment was successful. Let me see whether it becomes successful now. Let me see, where is the hole? Where is the hole? Where is the hole? No, this hole is not properly done. So when you make a hole in the plastic bottle properly and smoothen it out, the hole is, I cannot close it very well. That's the reason why it is not happening every time. Should happen. Why not happening? It's not falling. See, immediately I open, it falls down.
Okay, wonderful.
So this
Successful.
air pressure, normal atmospheric pressure plus the water pressure is more than the pressure upward. Okay.
Yeah.
So when I open it, this pressure becomes normal atmospheric pressure plus this pressure is more than the pressure upward, it falls down.
Yes.
Okay. So, so this is a very old experiment. Now I think I should stop doing experiments. Why do we teach air pressure in the schools? Because everything that we learn in school is used. You see, at every house, multi-storied house, we have got water tank up there, and there is a tank underground. The municipal water may come in that tank. Okay, when the municipal water comes by a pipe inside in the tank, which is underground, and there's a pump, a centrifugal pump. The centrifugal pump, what it does, it creates a vacuum inside. When it rotates, there's a vacuum is created, and then it draws up the water, and you can then that pump can raise it up to say 100 stairs also. It can be raised, but the height, there are a lot of experiments. I can't show all the experiments. I show that also, that 34 feet of water, 10.3 meter is the maximum suction height that can be sucked, because when the vacuum is created, and that vacuum, the air pressure forces the water up. When the vacuum is created inside the centrifugal pump, then the pipe, which is called the suction pipe, which is inside water, the air pressure forces the water up there into the pump, and that goes up. So whatever we learn, that is, when I read magnetism, the fan is working, there is a magnet. The light that we are having, there is magnetism. We'll do a few experiments on magnetism now. Let us see how much time we have. How much time we have now?
We've got around 10 minutes, sir.
Only, okay.
15 minutes. 15 minutes on clock.
15 minutes, okay.
Yeah.
Come quick. Give me the. এগুলো সরাও, এগুলো দরকার নেই, এগুলো ওদিকে রেখে দাও সব. So I shall now. আচ্ছা, ওটা পরে, হ্যাঁ, এটা পরে হবে. Okay. Now let me show you first. There are two exactly looking same two iron objects, but one is a magnet and one is iron. One is a magnet, the other is iron. Okay. And I shall give you only 5 seconds, 5-second time. 1, 2, 3, 4, 5. And by that time you have to tell me, by doing some experiment on this, you have to tell me what is the experiment that you have to do to find out which one is a magnet and which one is iron. Tell me. I shall start counting, only 5 seconds to think. Ready? 1, 2, 3, 4, 5. No more time.
Okay.
What I should do?
We've got an answer. One is look for iron filings. The second one is suspend freely using thread.
No. I have nothing else other than this.
Okay,
This two only. Nothing else is there.
Okay, that's the clarity over here. So repulsion is the true test for magnetism. So
no, in iron and in an iron and a magnet, there can be no repulsion.
Oh yeah,
there will be only attraction, nothing else.
Exactly, huh? Exactly.
No. So, very simple. That is what you teach. You place the magnet, place anyone at the center of the object. If it attracts, then this is iron and this is magnet. But if it does not attract, this is magnet, this is iron. Because for a magnet, the central region is called neutral region. You remember that? Neutral region. Yes. There is no attraction. See, there is no attraction. But when it is iron, if it attracts, that means it is iron, this is magnet. But if it does not attract, this is magnet, this is iron. So simple. So when you teach them the properties of a magnet, then you give such problems to a child so that one can apply their mind to understand. So experimental activity, doing science is so important. So that is the reason why the Chinese proverb says, I read, I forget. I see, I remember. I do, I understand. Science is doing. Okay? This is first of this experiment. Then line supports, bring the line supports. Let me see, because there's not much time. Achha. So you know that we teach the students that when you have a magnet, then all around this there is a magnetic field.
Yes.
And it is conceived that there are lines of force which starts from the North Pole. So this is the North Pole. This is the North Pole. This white portion, North Pole. It goes to the south, and through the body of the magnet, the lines of force are a complete path, north to south. Now you see a wonderful. I have already prepared it. See the lines of force. Come on. Okay.
So
you will see just now.
Can you put a book, sir?
You will see it just now. Don't. He is just turning. He is just turning the edge so that you can all can see.
Wonderful.
Can you see the now the iron filings?
Yes.
Arranged in lines.
Yes.
Can you see the iron filings?
There's a circular pattern, and
you see the iron filings are there. Iron filings are there, which I have sprinkled iron filings around the magnet, and you can see there at this point at the two ends the attraction is much more, and all the lines you can see so well, so nicely. What I have done very lightly, I have put the iron filings very lightly. If you put a lot of iron filings at one place, it is difficult. So put it very slowly, and then you will see that they arrange in lines. Okay, so these are lines of force which are complete path. It starts from the North Pole, ends at the South Pole, and all over. It's three-dimensional. All around the magnet, there's a magnetic field. As you go away, the magnetic field, the strength decreases. Okay, so there are formulas and all these things that you will learn in the class 11, 12. Okay, fine. Now, next is okay. All right. Now I shall show you another one by which you can also show, for which I shall take something else. Get the books here. Get the books here. No, you can turn it around. Turn it around. It's a book. Can you see the magnet now? I am showing you the magnet.
Yes, sir. It is on the book.
Achha. Now, what you do, I have got here. Just a village. Yes.
Yeah, this is more clear. Yes.
Can you see the magnet now?
Very clear.
Now, I have got button magnets. These are called button magnetic compass. Achha. I have got button magnetic compass. I put the button magnetic compass all around. See how they arrange themselves. Can you see that they have arranged themselves? Here at this place, it is parallel to the magnet, because North Pole and the South Pole is attracting the two ends of that button magnet at the same force. So it is parallel. But
also the compass shows the direction of the magnetic field.
Yes, sure. If you keep it there, if the no magnet is there, then it will show north-south. It shows north-south. So, but then if this is the North Pole, so it is attracting the South Pole. But as it goes there, the attraction of the North-South Pole is also taking place. So you see the change that is taking place, and at the middle, both North and South Pole, they're attracting at the same force. So this is parallel to the magnet. So this with the button magnets also, you can show if you have got 20 button magnets, which is very cheap, you can explain also the principle. Okay. Now, very often what happens that the polarity of this changes. Polarity of the magnetic compass changes, and you can change the polarity of the compass also very easily. And that I have found it so difficult for the teachers to do that. Let me show you something else now. This is the two experiments shows the magnetic lines of force. Now, I shall show you. Next, what I shall show you is. Oh, it's here. Okay. Next, what I shall show you is, acha, I have a blade. Give me the blade. There's blade here. I can make the blade. What happens to the blades? এখানে ছিল ব্লেড গুলো এখানে রেখেছিলাম আরে the blades were here the পাশাপাশি রাখলাম তো কোথায় গেল the blades were here there are two blades okay it has fallen down okay now you see I have got here let me show you first the magnetic needle. This is the magnetic needle. And magnetic needle is showing north-south.
Yes.
This is north, this is south. Okay.
Okay.
Now, if I take a magnet, say this is a magnet, and this is North Pole. Can you see the North Pole? The white spot? White spot? Can you see the white spot?
Yes, sir. Yes.
Yes. So I take it near the North Pole of this magnetic needle. See what happens? I take the North Pole, it is repelled. Okay? I show you again.
We weren't able to see the magnet when you were.
I know. I am taking it. I am taking because if I take it very slow, I am taking it very slowly. You see,
Okay.
and you see how it. You can't see the magnet now. I am taking it very slowly, but you see that needle is deflected. Can you see the needle going away?
Yes, sir.
So North Pole and North Pole repels. There are experiments for that. I am not showing all those experiments. Okay.
Exactly.
So now, how to magnetize a iron object? That I shall show you. You see, in the books it is shown that you give so many. You take the magnet, you take the iron piece, and then go on doing. It says take 20 times. No, if you take only once, then if it is a strong magnet, if it is strong, it's just a bar magnet, ordinary strong bar magnet. And if you just rub it just once or twice, it becomes a. I have started with North Pole. Tell me, I have started North Pole here.
Okay.
Can you see my finger?
Yes, sir.
So tell me, I take North Pole here, hold it here, and then rubbed it twice. What polarity? This will become a magnet. I shall show you that it will become a magnet. What polarity will be here? If I start with North Pole, you have not done it. Let us see what happens. So I am taking this. I started with North Pole here, and I take it near the North Pole. See what is happening. What is happening? Repelling.
It's
It
repelling.
will
Yes.
become North Pole. So if you start with North Pole, it will become North. Now I can
Yes.
easily change the polarity of this. What I do, I start with the South Pole. This is North Pole. I start
Yes.
with South Pole. See what happens. I have rubbed it twice.
Okay.
Let me rub it once more. I have rubbed it, started with South Pole here. Okay, now I shall take it before the South Pole, see what happens. See, it's repelling. It's repelling. That
Yes.
means I start South Pole, it becomes South. So easily I change the polarity of a magnet. But this is a thin piece of iron. So can change it. But this iron piece, you can't change the polarity so easily. You can't change the polarity. You see, in the sometimes way it is, it's not written that you have you rub it with another polarity will change. It doesn't. If it is a pin, if it is a blade, it's very thin. That can be changed. So polarity can be changed so easily. So how to make a magnet also you have understood with a simple magnet, bar magnet, and a blade or a pin, just a pin you can show. That is what I really wanted to show you. Now the next one Next one is, Acha, now give me that, okay, it's here, it's here.
Sir, I think we've lost the connection. Hello. Sir, I think we've lost the connection. Hello. Sir, are you there?
Can you see the test tube with trial inside? These iron filings are presenting as if they are molecules, And I have this bar magnet. This is the bar magnet, and the spot shows the North Pole. Now, I am keep making it the haphazard. I have second it. Now I take it near the magnetic needle. Both sides is attracted because this is iron and this is a very feeble magnet.
Yes.
But okay, now what I do, I take the magnet, I take North Pole and start rubbing it twice or 3 times. Let me rub it 3 times. Now see what will happen. Now I have started North Pole. I bring it near the North Pole. Attracted, repelled. So this has become north.
Yes.
So it is attracting the south and it is repelling the north. The force is so small, you see, it's repelling.
Yeah.
That means this has become a magnet now. Just the way I had magnetized the blade. The same way, now I make it again haphazard.
And that is a glass test tube, right?
Huh? This is glass, just glass or plastic test tube also will do.
Okay.
And you take iron filings inside, you close it by paper here, okay? And then you just rub it once to explain that each iron filing represents as a molecule. And when I rub it, they arrange themselves in proper line. Then you can show that figure that you see in the book. Give me that. This is there in the book. I shall show you that figure. Oh no, it's just a minute. Yes, here, there. Just you can see just a minute. Here. This picture you remember, this their book.
Okay, we can see it.
When it is just an piece, it is this. When you rub it with the magnet, when you rub it, it arranges themselves in line. You start with North Pole, then North Pole, and the side is the South Pole. It's there in the book. But when you do such an experiment, as I did, and then explain this, it will be easy for the children to understand. The domain and other things that you read in the book in extent as well. But simple experiments be done in the classroom to improve the understanding. My experience with more than 300, not 100, I have done more than 300 workshops with the team all over India. From Kashmir to Andaman and from South India to North India. And what is my observation is all learning is rote learning. Understanding of science is not taking place. That is the reason why in India we can't produce a mobile. We can't produce. There's very simple gadgets we have to import from either from Finland or from China or from any other place. We can't do it because our understanding is not taking place in science. If we can do that, then things will change. But then not only the science, but science and society has to be brought together. What changes science is making in technology and what technology is doing so far as our consumer life is concerned, that is what I shall talk about at between 5 and 6 today. I shall talk about that. There'll be another program like this. Okay. Now, this is what I have shown you as molecular magnetism. Now I show you, now that one. Now you have to teach Oersted's experiment. For that, what is needed is just a magnetic compass. This is a magnetic compass, and this red portion. Can you see the red portion that is showing the north?
Yes, sir. Yes.
North and south. And I am taking a piece of this insulated copper wire. Okay, and my granddaughter is helping me to keep it parallel to the just over it. Yes, just over the magnetic compass, and then I have got this battery. Then I shall pass current through this. And see what happens to the magnetic needle. Needle is now stationary. Now I put current over it. See what happens. The North Pole comes towards me on the left side. See?
Yes.
Now we keep it at the bottom. Now keep it at the bottom. Now I keep the wire at the bottom and then put it again. See which side the North Pole goes. It goes to the right.
Yeah.
To the right.
The opposite side. Yes.
Okay. Now then, hold it. On the top it was this direction, on the bottom it is this direction. And we have shown already that lines of force are complete paths. If the lines of force is like this here and like this there, what will be the nature of lines of force around the carrying, when the current carrying conductor? What will be the nature of the lines of force? It has to be a complete path. How it can complete the path? By concentric circles. The lines of force are concentric circles. Okay? So it is moving this direction, it will move this direction, it will move this direction, depending upon how you keep this. Okay? I keep it over a magnetic compass, and by that I can show Oersted's experiment. Now the other one, give me that. Give me the. Be careful. Give me that. Here. Now here I have a galvanometer, and I have here also I have copper wire, nearly 30-40 tons. Here it is given here, 30-40 tons of insulated copper wire. Now the needle is stationary. Can you see the needle?
Yes.
So now it is stationary. Now I take a magnet and I move it. See, the needle is moving. Can you see the needle moving?
Yes, sir.
That means the current is produced, and that current is now moving this one.
Yes.
The galvanometer is moving. The pointer is moving because of the. Now I keep it inside. It does not move. Does it move?
No, we don't see a movement.
But when I move it, it moves. So when there is a changing magnetic field inside the coil, there is a current is produced. Okay. When there is a change of the magnetic lines of force or magnetic force in a current conductor, a current EMF induced in it, and that gives the current. Okay, but if I move it very fast, that rate is very high, then current is more. But if it is slow, the current is less. That is Faraday's laws of electromagnetic induction. When there is a change in lines of force, there is inducement, and amount of current will depend upon the rate of change of magnetic flux. When it's moving fast, then the rate is high, then current is more. Okay, the current that we are using the fan, the light today, because of Faraday, and he was a blind. He was a bookbind, and when the books were coming to him, he was looking. Then he used to attend that famous institution, Royal Institution, sitting at the back. Then the director of the Royal Institute saw this boy joining the meeting, and that boy later on became Michael Faraday. Michael Faraday. And the last one I shall show now. Last one. Huh? Oh, it's not. Can I show the last experiment?
Yes,
can I show the last experiment?
Yeah.
Or we'll close?
Yeah.
We'll close.
You can.
Okay. Okay.
Yeah.
Okay. I would like to thank Harper Collins for giving me this opportunity to talk to. I don't know how many teachers are seeing it, but I'm so glad that I could show you the teachers all these experiments that I have shown. But it takes really 2 or 3 days to show all the experiments. And here in this, we are 3 or 4 in India who go around all over India. Dr. B.N. Das, Dr. Birendranath Das, who is also looking at this program most probably. Dr. B.N. Das, he was a professor of a college. He was teaching in the Presidency University here. He and me from Calcutta, we are going around India and showing this. And that experience I got while I did this program between 83 and 1988 for 5 years, the Quest program, that gave me the joy of working with hand, doing simple experiments with low cost, no cost material. And thank you, Harper Collins, and special thanks to Ahona Bhattacharya, whom I know very well for a long time, Ahona, thank you for calling me and doing this experiment. Okay, thank you. Thank you all.
So on behalf of Harper Collins and also the 400 odd teachers odd teachers, students, and also perhaps even parents of them that attended this session, we would like to thank you for inspiring us in many ways. I mean, we learned how to recycle objects. That's one, perhaps with the syringe and also the bottle, the plastic. The second thing is to learn from experience.
Yes.
And that inspires us to do the Make in India program, in fact, right? And the third thing is the energy. I think you're the youngest 89-year-old in the world.
Young man.
Yes, you're the youngest 89-year-old in the world. So thank you so much for having inspired us for so much time. You were belligerent, you were unstoppable. So you love your work. And this is the kind of people that any human being would like to meet to feel inspired. So thank you so much and wish you a happy weekend. And the same goes to everyone. Wish you all a happy weekend and a safe weekend in that. So all of you stay safe and stay healthy. Thank you so much.
Thank you. Thank you all. Thank you all.
Thank you.